Long before the James Webb Space Telescope was ever launched into space, humanity carried within itself a quiet but powerful longing to see farther, deeper into the dark regions where the universe's very first light once trembled softly. Hubble had opened a breathtaking doorway for us, allowing us to witness thousands of nebulae and countless galaxies shimmering in the distant night. But as time passed, it became clear that Hubble, magnificent enough to become an icon, still could not bring us close to those earliest moments after the Big Bang. To glimpse the universe when it was still young, we needed to capture light that had stretched into the infrared after billions of years of traveling. Hubble could only grasp a small portion of that ancient glow, and we understood that we needed a different pair of eyes, more delicate, more sensitive, designed specifically to observe this deep crimson light. From that longing, the dream of a brand new telescope began to take root. James Webb was never just a scientific project. It was a living testament to the perseverance of thousands of people across 2 decades. From the engineers who held their breath through every test, to the scientists who patiently refined each algorithm, everyone contributed a small piece to a much larger picture. Every component of Webb, from its golden mirrors to its sunshield, endured harsh trials to ensure they could survive the bitter cold and violent shaking of a journey beyond Earth. Many times, the mission seemed on the brink of collapse, with rising costs or sudden technical setbacks. But Webb was always kept alive, because no one wanted to surrender the chance to look into the dawn of the cosmos. When the hexagonal gold-plated mirror segments were finally completed, it became clear that Webb had taken one step closer to becoming real. Its 6.5-meter primary mirror, much larger than Hubble's, was designed not as a single solid piece, but as a structure that could fold like overlapping petals, waiting to bloom open in space. Combined with its ultra-sensitive infrared instruments, Webb could gather light from galaxies only a few 100 million years old after the Big Bang. Every detail, no matter how small, echoed a single aspiration: to reach the biggest questions of all. How the universe began, how the first stars formed, and whether life might exist somewhere beyond Earth. By late 2021, when Webb was finally complete and waiting for launch, a quiet anticipation swept through the scientific world. On that Christmas morning, the sky over the launch site in French Guiana felt unusually calm, as if space itself were pausing for the moment. The Ariane 5 rocket stood silent before igniting its engines, carrying Webb folded neatly inside its fairing. There were no loud cheers, no grand display, only a deep sense that humanity was about to step into a new era. As the rocket lifted off, its fiery tail glowed, reflecting sunlight off the metal shell. Webb was placed into orbit, and from there began its long journey of 1.5 million kilometers to the Lagrange point L2, where the gravitational forces of Earth and the Sun create a perfect balance, a place where Webb could remain steady in relation to Earth. Inside the spacecraft, Webb rested like a precious gift held with great care. Its giant sunshield remained folded, its 18 mirror segments locked in place, every instrument silent, waiting for the moment to awaken. Even from hundreds of thousands of kilometers away, humans watched its trajectory, trusting that decades of careful preparation would allow Webb to unfold perfectly and operate in flawless harmony. The significance of Webb's launch was not only in its engineering triumph, but also in the feeling that we were extending the reach of Hubble, pulling the thread of human understanding farther than ever before. Hubble had given us images that stunned the world, helping us understand the age of the universe and the birth of stars. But Webb wasn't simply a continuation. It was more like a torch being passed forward, brighter, farther reaching, toward the moment when the universe's first light was gently kindled. As Webb drifted through space, every minute felt stretched, suspended. Worry mingled with hope, making time feel almost fragile. The first commands were sent, and the mirror segments prepared to unfold, like a slow, deliberate performance where every movement mattered. There would be no second chances. The distance was far too great for repairs, unlike Hubble long ago. For this reason, every step had to be perfect, every mechanism faultless. From the faint dream of the 1990s, when humanity first imagined a giant infrared telescope, to the moment Webb left Earth in 2021, that span of time held decades of patience, belief, and reverence for the universe itself. Webb stands not only for technology, but for our yearning to reach the distant, to uncover the quiet stories waiting in the endless dark. After its long journey away from Earth and toward the L2 point, the story from before continues to unfold, guiding us to the next crucial moment. The instant when Webb truly stretches itself open before the vastness of space. From a dream that spanned 2 decades, Webb now begins transforming into a complete living instrument, carrying within it the intricate structures humanity so carefully crafted. Every part of the telescope was designed not only to survive the harsh conditions of space, but also to unite into one of the most sensitive systems ever built, capable of gathering light that has been stretched across more than 13 billion years. The most striking and recognizable feature of Webb is its 6.5-meter gold-coated primary mirror. This mirror isn't a single piece. It is a mosaic of 18 hexagonal segments made of lightweight, yet incredibly strong beryllium, each coated with a layer of gold only a few hundred atoms thick. Gold was chosen not for beauty, but for its ability to reflect infrared light, the oldest light Webb was created to capture. When you look at the mirror, it feels like a giant pattern arranged with millimeter-level precision. Even resting in the darkness of space, the structure seems to radiate a quiet warmth, as if carrying within it the memory of the universe's earliest light. From the beginning, Webb's primary mirror couldn't be launched fully expanded. Its size far exceeded the rocket's fairing. So engineers designed a multi-folding mechanism that allowed the mirror to tuck itself neatly together, like petals wrapped inward. Only once in space could Webb slowly unfold each segment, aligning them with tiny actuators to achieve the needed precision. A misalignment smaller than a strand of human hair would distort the incoming light. And yet Webb succeeded, because each component was built with near-perfect accuracy. Beyond the mirror, Webb carries another equally critical structure, its giant 5-layer sunshield, each layer roughly the size of a tennis court. 5 sheets of ultra-thin polyamide film are held taut by lightweight struts, forming a thermal barrier capable of reducing more than 300 degrees of heat between the side facing the sun and the side turned toward the cold of deep space. Thanks to this sunshield, Webb's sensitive infrared instruments can stay at the extremely low temperatures needed to detect the faint signals from the distant universe. Without it, every observation would be drowned out by the telescope's own heat, making it impossible to see through the darkness of time. In space, Webb's deployment unfolded slowly, step by step, like a carefully choreographed mechanical dance. First, the sunshield was pulled open, each layer separating from the next, to create the spacing needed for heat to disperse. Every pull point and tensioning cable was controlled from Earth, with commands sent across hundreds of thousands of kilometers. There was no room for mistakes, and no chance for repairs. Everything had to work perfectly the first time. After the sunshield, the outer mirror wings began to open. Each hexagonal segment rotated into place, joining the others to form a flawless curved surface. Seen from afar, the sight resembled a golden flower blooming gently against an endless, dark backdrop. But the mirrors didn't just unfold. They needed microscopic adjustments through actuators on their backs, moving in increments smaller than the width of a single atom. Only after those adjustments were complete did the primary mirror become a unified whole, ready to receive light from stars billions of light years away. At the same time, the secondary mirror, a small circular structure held at the end of 3 long support struts, moved into its operational position. This mirror collects the focused light from the primary and directs it into the instruments inside the telescope's body. The mechanism demands extraordinary stability. Even the slightest vibration could nudge a target out of the frame. Deploying the secondary mirror was one of the mission's most critical steps, and once it locked into place, Webb officially became a functioning telescope, rather than a folded machine drifting through space. When every mirror segment had opened and been precisely aligned, when the sunshield had stretched into its perfect shape, Webb was almost awake in the darkness of the cosmos. Light from distant galaxies began touching the gold-coated surface, bouncing through the optical path and into the sensitive infrared instruments deep inside. The earliest signals were faint, but their meaning was immense. They carried the glow of newborn stars, the shimmer of gathering dust and gas, the whispers of galaxies formed when the universe was still young. Webb was built to see these things, and now it could. With a sensitivity unlike anything before it, from the giant golden mirror to the layered sunshield, from the delicate folding mechanisms to the 1.5 million kilometer journey, every detail of Webb reflects what humanity longs for: to reach the farthest edges of the observable universe. Webb is not just a technical instrument. It is a symbol of persistence and imagination. A reminder that even from a small planet, we can create windows that look through the darkness of time itself. After Webb's enormous golden mirror had been fully assembled, and its multi-layered sunshield stretched smooth in the cold emptiness of space, the mission moved into a new chapter. The final deployment steps from before became the foundation for Webb to begin its most essential phase, refining its optical system and preparing for its very first glimpse of the universe. From a complex mechanical structure drifting through space, Webb gradually approached the state it had been built for, the state in which it would truly see the cosmos through its infrared eyes. The calibration process began with the extremely precise alignment of the hexagonal mirror segments, so that all 18 could function as a single mirror. Light from distant stars served as reference points, and each segment was adjusted using control mechanisms so small they defy intuition. Each mirror moved by distances smaller than the width of a molecule, until they ultimately merged into one seamless reflective surface. From there, the light followed its proper path: primary mirror, secondary mirror, and into the instruments. As the optical system neared completion, Webb's infrared instruments were cooled to the temperatures they required. These sensors must operate even colder than the space around them, so that the heat they give off doesn't interfere with the signals they are trying to detect. At this stage, the 5-layer sunshield revealed its full importance, protecting Webb from the heat of the sun, Earth, and even its own components. Thanks to it, Webb could observe the faint light that had traveled for billions of years, the kind of light that carries the stories of the universe's earliest epochs. By mid-2022, after months of deployment and careful tuning, the first imaging signals appeared. They were not yet full photographs, but small samples of light. Early signs that the system was working exactly as intended. Webb then continued through multiple rounds of refinement, each stage sharpening the images further. Once every parameter reached flawless precision, Webb was ready to send its first images back to humanity. That moment wasn't a sudden burst of excitement. It was more like a soft glow spreading slowly after a long night. The first set of images showcased several targets, but the most breathtaking was the vast scene of the Carina Nebula. In the image titled "The Cosmic Cliffs," Webb revealed enormous structures of gas and dust rising like jagged mountain peaks, though they were actually clouds of hydrogen and interstellar dust, where thousands of newborn stars were forming. The tiny specks of light scattered across those cliffs were young stars igniting after gathering enough material. Before Webb, most of these lights were hidden behind dust, but with its infrared vision, Webb saw straight through the veil and captured what was happening inside. Beyond Carina, Webb turned its gaze to a distant galaxy cluster, where galaxies receded deep into the past by billions of years. The light from these galaxies had stretched so far that human eyes could never see it. Yet Webb captured every detail, every swirl, every filament, every gentle interaction. The resulting images were more detailed than anything any telescope had ever shown before, creating a sense of peering into tiny jewels floating across an infinite ocean. One of Webb's most unexpected achievements during this early phase was obtaining the spectrum of an exoplanet, allowing scientists to identify the chemical makeup of its atmosphere. When light from the host star passed through the planet's atmosphere before reaching Webb's detectors, the telescope analyzed its absorption features. In the first data, Webb revealed signs of water vapor in the atmosphere of a hot exoplanet. While water vapor alone doesn't confirm life, its presence is a key indicator, proof that Webb could analyze distant atmospheres with unprecedented sensitivity. Every image, every piece of data, every spectral line carried significance far beyond itself. Together, they confirmed that Webb had truly opened its eyes. After a long and intricate deployment and years of design and testing, Webb finally began the mission humanity entrusted to it: to peer into the farthest shadows and search for the universe's story from its earliest dawn to the present moment. When the first images were released and spread across the world, the feeling that followed wasn't loud or explosive. It was quietly profound. Nebula structures glowed like paintings made of starlight. Distant galaxies appeared as tiny specks holding entire eras within them, and the detection of water in an exoplanet's atmosphere made people feel that exploring the universe on a deeper level had truly become real. Webb doesn't just look farther than Hubble, it looks differently. If Hubble painted a glorious portrait of the universe in visible light, Webb reveals the deeper layers, where the oldest light whispers secrets hidden for billions of years. With Webb, humanity has moved closer not only to the era when the first galaxies were born, but also to understanding star formation, galaxy evolution, and the nature of worlds far beyond our own. These first images are only the beginning. They are like a gentle but confident greeting, confirming that Webb is ready to open a new era in humanity's exploration of the cosmos. Space may be vast and silent, but with every observation Webb makes, the distance between us and those distant mysteries grows just a little smaller, until the things once imagined only in dreams take shape as real images before our eyes. After Webb had opened its eyes and sent back the first faint signals, as described before, the journey moved into an even more important moment. The moment when its first complete images were released. images that were not only scientific data, but profound works of cosmic art. From the delicate light Webb captured early on, it now began delivering images so deep and nuanced that the entire world stopped to look. They did more than demonstrate what the new telescope could do. They revealed the universe's vast, quiet, and intricate beauty. Among these early images, the very first deep field, SMACS 0723, was an unforgettable milestone. Webb focused on an incredibly small patch of sky, no larger than a grain of sand, held at arm's length. Yet inside that tiny fragment of the heavens, thousands of galaxies appeared in crisp detail. Each galaxy holds billions of stars, and the light from many of them had traveled for billions of years before reaching Webb. Thanks to the sensitivity of its infrared instruments, Webb also captured gravitational lensing, where enormous masses warp space-time itself, stretching the light from background galaxies into soft, silky arcs. These arcs aren't distortions. They are the signatures of curved space-time, a quiet confirmation that Einstein's theory of relativity still holds true, even in the most distant corners of the universe. As Webb observed SMACS 0723, it showed that although the universe is immense, it can reveal itself in astonishing detail if we simply look patiently in the right direction. The oldest light, once stretched thin by the expansion of the cosmos, now appeared as faint but remarkably persistent signals. They whispered about the structure of the young universe, about how galaxies gathered into clusters, about how the first stars began to take shape. And in that single image, viewers could almost feel the slow, endless calm of space itself, like a breath drawn over billions of years. From SMACS 0723, Webb shifted its gaze to something closer but no less breathtaking: the Southern Ring Nebula. This is the remnant of a dying star approaching the end of its life. After exhausting its fuel, the star swelled and shed its outer layers, creating rings of dust and gas expanding outward. In visible light, the nebula was already beautiful. But through Webb's infrared view, its layers appeared with an ethereal clarity, thin veils stacked gently upon one another, each layer the trace of a different phase in the star's fading life. What made Webb's view extraordinary was not only the detailed shells of gas, but its ability to clearly see the dying star at the center, something that had been hidden from other telescopes. Webb revealed that the central star was not alone. It had a companion. The two stars orbiting each other had sculpted the nebula's distinctive structure. In the image, every fine detail stood out with staggering clarity. The delicate rings of dust, elongated wisps of gas, and even the tiny points of background stars shining through. Together, they formed a drifting tableau suspended in space, gentle in appearance but rich with scientific insight into the final stages of sun-like stars. Leaving the nebula behind, Webb continued by sending back its image of Stephan's quintet, a group of 5 galaxies interacting with one another. 4 of them are truly close together in space. The 5th only appears nearby from Earth's point of view. Still, in Webb's image, all 5 galaxies came together in a single dramatic composition. Fine, misty streams of dust stretched across them like cosmic tides, revealing the gravitational forces at play. Some galaxies looked as though they were nearing collision, or at least pulling and reshaping one another in ways too slow for human eyes. But perfectly traceable in infrared, Webb captured starbursts, hot gas clouds, and regions of intense star formation glowing within the darkness. The faint red glows marked dense dust regions impenetrable to visible light, but transparent to infrared. That allowed Webb to peer through those cocoons and witness the stories unfolding inside. Newborn stars igniting, hot gas curling along gentle arcs, and the remnants of ancient supernovae scattering like glimmers of memory across space. These first images did more than prove Webb's capability. They stirred a sense that the universe is not cold and empty in the way it is often imagined. Instead, it appeared like an enormous painting, built from deep colors, soft shapes, and slow motions stretched across time. Webb did not simply look farther, it revealed the beauty of what lies closer too. From the dust rings of a dying star to galaxies tugging at one another in the dark, every detail became part of a vast, wordless symphony played across the cosmos. And so, when viewers gazed at this first collection of images, they felt not only the grandeur of space, but a sense of standing before an open doorway into a dream. Webb, in its own way, had turned the silent void into a gentle film, one where every glimmer of light carried a quiet message about patience, endurance, and the lasting beauty of the universe. After the first breathtaking images, those cosmic paintings described earlier, the story of Webb naturally widened, as if the views of radiant nebulae and nearby galaxy clusters had guided humanity's gaze even farther, beyond present beauty, toward the deeper layers of time. From the familiar structures of the nearby universe, Webb began turning its mirrors toward the distant past, where the faintest light of the very first galaxies still drifts in darkness. The dazzling images of SMACS 0723, the Southern Ring Nebula, and Stephan's Quintet were only the surface of the iceberg. Beneath them lay stories far older, and Webb was born to see those stories. The universe, vast beyond comprehension, still has an age, a beginning. The first moments after the Big Bang were when every particle of light began its journey across billions of years. When Webb targets the most distant objects imaginable, it is not just looking into space, it is looking into time itself. The galaxies Webb observes at extreme distances do not appear merely as tiny points of light. They are relics of a newborn cosmos, places where matter had only just begun to gather into the first structures. Every image Webb returned in this phase felt like a fragment broken off from the very beginning of everything. Among the most astonishing discoveries were galaxies formed only a few 100 million years after the Big Bang. Astronomers had predicted such ancient galaxies might exist, but no one expected them to be so numerous, so bright, or so early. Webb challenged theoretical models because these galaxies seem to have evolved faster than previous predictions allowed. For many scientists, it felt like opening a door into a chapter of the universe that had existed only inside simulations. One of the most striking examples is MOM Z14, a galaxy with a redshift so high that its light was emitted when the universe was only about 280 million years old. Compared to today's 13.8 billion-year cosmos, 280 million years is like the first few seconds if all cosmic history were compressed into a single day. The light Webb captured from MOM Z14 had traveled through expanding space, stretched so far that it landed deep in the infrared. Without Webb's sensitivity, that light would have remained forever swallowed by darkness. And it wasn't just MOM Z14. Webb discovered many other galaxies from that same era, many of them brighter than anyone expected. Why were they so luminous when the universe was still so young? How could they have gathered enough material to form so many stars in such a short time? These questions didn't diminish Webb's impact. They proved that Webb was truly exploring untouched cosmic territory. These cosmic surprises pushed astronomers to reevaluate models of early galaxy formation and even consider adjusting humanity's understanding of how quickly the young universe grew. By observing these distant galaxies, Webb was doing something that once seemed impossible. It was looking through time itself. Every photon Webb captures is a message sent from a faraway era, an age before the sun existed, before the Earth formed, before any planet in our solar system even took shape. Those ancient rays were born from the first stars, huge, brilliant stars that lived fast and died in spectacular explosions. Their supernovae scattered the first heavy elements beyond hydrogen and helium, elements that later formed new stars, new galaxies, and new planets. Eventually, on one small blue world, life emerged, and from life, consciousness. And from consciousness came Webb, built to look back at the source of its own existence. Thanks to Webb, we can imagine a universe that looked nothing like it does today. No elegant spiral galaxies like the Milky Way, no glowing star clusters, no massive multicolored nebulae. Instead, the early universe was a vast darkness sprinkled with faint, primitive galaxies that had only just formed. Those galaxies were small and loosely shaped, lacking structure, but inside them burned the first generation of stars, the original lanterns that lit the primordial night. Webb didn't just photograph these ancient galaxies. It analyzed their spectra, revealing their chemical makeup, their estimated ages, and their star formation rates. Some showed enormous populations of young stars, indicating they were in a rapid starburst phase, explaining their unexpected brightness. Others showed signs of cosmic dust, which is formed only from dead stars. That raised another question. How had the early universe already produced a first generation of stars, allowed them to die, created dust, and then formed a second generation, all within less than 300 million years? These mysteries didn't feel like contradictions. They felt like reminders that the universe always holds deeper layers than we imagine. Webb was approaching the very edge of the observable timeline, inching toward chapters no telescope had ever touched. Every ancient galaxy Webb found felt like a memory falling out of the universe's earliest pages, its light now captured by an instrument built by living beings on a small, fragile planet. And so this chapter closes with a quiet but immense feeling. Webb is touching moments closest to the beginning of everything. It isn't just observing the universe, it is observing time. It isn't merely seeing distance, it is reading the memories of space itself. With Webb, humanity has carried its vision to the brink of cosmic time, to the place where the universe's earliest light still drifts in the dark, waiting for someone to listen. After Webb brought humanity closer to the dawn of the universe, back to the moment when the first galaxies flickered into the primordial darkness, its gaze naturally widened toward another question, just as ancient. If Webb could look back to where the universe was born, could it also look toward places where life itself might be quietly unfolding? From the traces of the early cosmos that Webb had unveiled, the story continued into a new realm of discovery, where light did not describe the birth of galaxies, but the fragile breath of distant worlds that might carry life. Webb is not just a telescope designed to peer into the early universe. It is also the most powerful tool ever created for studying exoplanets, worlds that orbit stars other than our sun. In the years before Webb, scientists had already discovered thousands of exoplanets through telescopes like Kepler and TESS. But knowing these planets existed was only the first step. What humanity truly longed to understand was what their atmospheres contained, whether they held water, organic molecules, or any hint that life might form there. To answer those questions, we needed an entirely different kind of vision. eyes sensitive enough to analyze starlight that had filtered through the thin atmospheres of tiny, faraway worlds, tens, hundreds, even thousands of light-years away. Webb was born to do exactly that. When an exoplanet passes in front of its host star, the star's light is filtered through the planet's atmosphere before reaching Webb. Every molecule in that atmosphere absorbs light in its own unique way, creating a distinct spectral signature. Even the faintest trace of that filtered light, once it touches Webb's golden mirror, can be analyzed by its infrared instruments to reveal what the atmosphere is made of, even if the quantities involved are almost unimaginably small. Webb's first observations of exoplanets quickly surpassed expectations. One of the most striking results was the detection of water vapor in the atmosphere of a hot planet, orbiting very close to its star. Though such a world is far too hot for Earth-like life, the mere detection of water vapor proved that Webb's precision had reached a rare and extraordinary level. Beyond water, Webb also recorded carbon dioxide, methane, and other organic molecules in the atmospheres of multiple planets. These molecules are not direct evidence of life, but they reveal that throughout the cosmos, organic chemistry is far from rare. Webb also began studying smaller, rocky planets, those closer in size to Earth. These are the truly promising targets because rocky planets in the right zone around their stars, not too hot, not too cold, may support liquid water. And liquid water is the foundation of life as we understand it. Though analyzing the atmospheres of such small planets is incredibly challenging, Webb has already begun doing what earlier telescopes could not, detecting faint chemical signatures on these worlds. Even though these early results require further confirmation, Webb has opened the first doorway, not only proving that rocky planets exist in the right zones, but that their atmospheres may be complex. In many observations, Webb has also detected planets with clouds, haze, and thick layers of gas like curtains wrapping their worlds. Every cloud layer and trace of vapor reflects histories of temperature, wind, and atmospheric structure. These may be worlds very unlike Earth, yet still holding echoes of familiar processes. They show that the diversity of planets in the universe is far greater than humanity ever imagined. Thanks to Webb, the idea that humans might not be alone feels closer than ever. Not just a question whispered into darkness, but a possibility we can study, survey, and define through data. A planet with water, organic molecules, and a complex atmosphere could be a place where chemistry evolves in the same ancient way it did on early Earth. And if one such planet exists, perhaps a second, a third, and many more are scattered among the billions of galaxies. Though Webb has only been operating for a short time, its exoplanet discoveries already create the sense that a new era of exploring distant worlds is approaching. No one knows what Webb will find in the coming years. It might detect a powerful hint of life. It might uncover a strange chemical signature, unlike anything seen before. Or it might reveal something beyond our current imagination. What is certain is that Webb has many years ahead of it, with its ultra-sensitive infrared instruments and its stable position at Lagrange point L2, giving it a pristine view of the universe, free from Earth's heat and light. Looking back across Webb's entire journey, from its early design to the unfolding of its mirror in darkness, to the first nebula images, to the ancient light of early galaxies, the study of exoplanets feels like another kind of milestone. Not a look toward where everything began, but toward where life might be unfolding now. One side is the ancient past, the other is a possible future. And Webb stands between them, a bridge connecting origins and hope. The final movement of Webb's story settles into a gentle, lingering truth. Thanks to Webb, humanity's vision no longer touches only the edge of space. It now reaches the edge of our deepest questions about existence. One day, the faint signals Webb gathers may become a whisper, telling us that life is not the story of Earth alone, but a chapter repeated throughout the vast book of the universe. After the years in which Webb opened a doorway to distant worlds and planets carrying the possibility of life, the story naturally drifts back toward an earlier moment in the history of space exploration. A moment when humanity first dared to imagine that our eyes on the universe didn't have to remain tied to the ground. From Webb's ability to analyze the atmospheres of exoplanets, the idea of placing a telescope beyond Earth's atmosphere reappears as a foundational turning point. Because if Webb is the hand reaching into the future, then Hubble is the place where the first door opened, where we first learned to understand the sky in an entirely new way. Looking back at Hubble is like looking back at the origin of a whole era of space-based astronomy, where dreams once thought impossible became real through the perseverance of people who believed the universe deserved to be seen more clearly. For centuries, those who studied the sky had to accept the limits of Earth's atmosphere. Air constantly shifts and ripples, distorting starlight and making stars appear blurred or dim. No matter how large or sophisticated a ground-based telescope became, it still had to peer through a restless curtain of air. So the idea of placing a telescope in space was viewed as bold, almost impossible. Yet that very impossibility inspired scientists to make it real. They believed that if they could lift a telescope above the atmosphere, the light from galaxies, nebulae, and stars would appear with a clarity no Earth-bound instrument could match. In the 1970s and 1980s, after many rounds of technical debate and planning, Hubble took shape on the drawing board as an extraordinary ambition. A large, stable space telescope capable of achieving a level of resolution unmatched by anything on Earth at the time. Every component was built to demanding standards because even the smallest flaw could jeopardize the entire mission. Everything had to function in microgravity, an environment with no air, no wind, and no easy way to repair anything for years. In 1990, after delays and fine-tuning, Hubble was launched aboard the Space Shuttle Discovery. It was the first time humanity placed a major telescope above the atmosphere, marking the beginning of a new chapter in our exploration of the sky. When Hubble separated from the shuttle and began operating, the world held its breath, waiting for its first images. Everyone expected unprecedented sharpness, nebulae in vivid detail, galaxies shining more clearly than ever before. But when Hubble's earliest images arrived, they were not what anyone hoped. The pictures were blurrier than anticipated. Stars appeared as soft, smeared halos. Analysis revealed that Hubble's primary mirror had a tiny flaw, off by no more than 1/10 the thickness of a human hair. Yet in astronomy, even an error that small is enough to blur every image. Instead of seeing this as failure, the scientific community recognized it as a challenge to overcome. Letting Hubble drift through space with a minor but devastating flaw was not an option anyone was willing to accept. Hubble had been designed to be upgraded and repaired by shuttle missions, and now that capability became essential. Engineers began planning an unprecedented repair mission, sending astronauts to Hubble to install corrective optics, a kind of contact lens for the telescope, to restore its clarity. In 1993, the Space Shuttle Endeavour carried a team of astronauts on a remarkable journey. For the first time, humans performed an optical surgery in space, replacing and installing crucial modules on the telescope. The corrective system rerouted light through the flawed mirror and then brought it back into perfect alignment. When Hubble resumed operations, sharp images began to appear immediately. Nebulae, galaxies, stars, and distant structures emerged in stunning detail. The repair was so successful that Hubble went from a mission at risk of failure to a symbol of determination and ingenuity. That repair was more than a technical triumph. It became a defining story of refusing to give up even when facing a tiny error with enormous consequences. Space allows no mistakes, yet humanity proved capable of fixing even the problems that seemed out of reach. Thanks to that effort, Hubble began its journey toward becoming one of the most important scientific instruments in human history. More than 3 decades have passed, and Hubble has observed millions of objects across the universe. But all of its achievements trace back to one simple idea: lifting a telescope above the atmosphere to see more clearly. That idea came with challenges, setbacks, and anxious moments. But once realized, it became a milestone in humanity's expanding vision. This section, then, opens the door to the story of Hubble, from ambition to trial to a historic repair, each part contributing to the making of a telescope that became the symbol of a new era in exploring the cosmos with eyes no longer constrained by Earth. After Hubble was successfully repaired in the 1993 servicing mission, the story from earlier naturally opened into a new chapter. Like a pair of eyes being given back their clarity and beginning to see the world with a sharpness that once seemed only a dream. From a project on the brink of failure, Hubble stepped into the most radiant years of its life. The moment its vision was corrected, laid the foundation for the brilliant 3 decades that followed. Years shaped not by calm, but by triumph, challenge, effort, and countless rebirths. All of it made Hubble one of the most vibrant scientific lives humanity has ever created. When Hubble sent back its first images after the repair, the world almost fell silent. The pictures were so sharp that any disappointment from before evaporated instantly. Nebulae that once appeared hazy now emerged in bold detail. Every strand of dust, every cluster of young stars, every distant streak of light etched clearly, as if a window to the universe had just been polished for the first time. From that moment on, Hubble wasn't merely an observational tool. It became humanity's widened vision, a window unobscured by Earth's atmosphere. Orbiting about 550 kilometers above the surface, Hubble circles Earth every 97 minutes. That path carries it through the planet's daylight and darkness over and over. One moment gliding above soft, drifting white clouds, and the next gazing out toward the deep, star-filled expanse. Every orbit is a new opportunity to observe. From its suspended vantage point, Hubble faces no atmospheric turbulence, no shimmering heat to bend the light, no tremors from the ground. Everything around it is still, cold, and crisp, allowing the telescope to gather the faintest glimmers from the universe's farthest galaxies. But keeping Hubble alive for 3 decades required far more than a single moment of effort. Unlike Webb, Hubble was designed to be visited by humans, and that design gave it a history unique among telescopes, a journey nurtured by human hands. Over 30 years of operation, 5 space shuttle missions traveled to Hubble to upgrade it, replace parts, install new cameras, refine its systems, and extend its lifetime. Each visit made Hubble feel young again. One mission gave it a more sensitive camera, another provided improved spectrographs. Sometimes its guidance systems were replaced, allowing Hubble to hold a steady gaze with even greater precision. On other missions, old batteries were swapped out to ensure years of power ahead. Each upgrade was like giving it a fresh breath. And because of this, Hubble didn't just survive its original lifespan, It continued writing history through humanity's patience and care. Year after year, Hubble returned images that captured the world, not only with their scientific value, but also with their beauty. Glowing nebulae like giant cosmic paintings, spiral galaxies sparkling with starlight, globular clusters shining like handfuls of jewels suspended in darkness. Hubble revealed scenes no telescope had ever captured with such clarity. That clarity changed the way humanity imagined the universe. The sky was no longer a collection of smudges or faint dots. It became a dynamic, colorful, structured realm, full of ongoing processes unfolding quietly within what once seemed motionless. Not all the years were easy. Every servicing mission carried risk. Space is unforgiving, and even a small issue could jeopardize everything. At one point, Hubble faced the possibility of being left behind after the space shuttle program neared its end. Many feared Hubble's life would soon close. But through persistent advocacy and careful planning, NASA approved one final servicing mission in 2009 aboard the shuttle Atlantis, granting Hubble the strength to continue operating even today. In many ways, Hubble is like a silent night watchman. Each orbit is another patrol. Each time it turns its mirror skyward, it listens once more to the universe. For 3 decades, Hubble has looked toward places human eyes can never reach. Dense clouds where stars are born, galaxies colliding in slow cosmic dances, supernova explosions like farewell messages from giant stars. It has watched massive planets move around distant suns, observed the rise and fall of interstellar clouds, and captured the unfolding drama inside nebulae. And in all these observations, Hubble sent back data that helped humanity understand how the universe evolves. Because of Hubble's persistence, tens of thousands of scientific studies have been published. It helped refine the rate at which the universe expands, contributed to the discovery of dark energy, and gave more accurate estimates of the universe's age. Its observations laid the groundwork for understanding the shapes, structures, and formation of galaxies. And all of this helped place Webb in its proper role, as a successor continuing the journey to the very edge of space-time. Today, even with Webb in operation and sending back stunning new images, Hubble continues its quiet work in its familiar orbit. It does not compete with Webb, it complements it. Hubble observes in visible and ultraviolet light, while Webb sees in deep infrared. Together, they create a fuller picture of the cosmos, 2 chapters of the same vast book humanity is trying to read. Through all its trials and triumphs, Hubble remains there, like an old friend who never left its post. It drifts in the darkness, patient and steady, watching the universe and whispering back the secrets only it can see from its place between Earth and the endless night. After all the ups and downs of its long journey, mentioned earlier from the first time its vision was repaired to the many upgrades that kept it alive, Hubble's story naturally opens into a deeper dimension. Beyond its years of operation and the support it received from shuttle missions, what remains after more than 3 decades quietly circling Earth is a lasting legacy. That legacy wasn't shaped by a single moment, but by millions of observations. Each time Hubble pointed its mirror toward the sky, another page was added to the longest journal humanity has ever written about the universe. From the early 1990s, when Hubble began sending back its sharp images, it transformed the way people saw the cosmos. It became not just a scientific instrument, but a cultural icon. Its images appeared in textbooks, magazines, educational materials, on computer screens, and in science fiction films inspired by real cosmic portraits. Few scientific instruments have ever become such a powerful visual symbol, familiar yet mysterious, reminding people of both the beauty and the smallness of our place in the universe. Throughout 3 decades of operation, Hubble has carried out more than 1.7 million observations. Each one is not just a beautiful picture, but also a trove of scientific data, helping us better understand the structure and evolution of the universe. That data has led to more than 22,000 scientific papers, an extraordinary number for any observational tool. This makes Hubble not only an engineering achievement, but a cornerstone for generations of astronomical research. Looking at the images Hubble captured is like reading a visual diary of the universe. A diary not written in words, but in starlight and galaxy light. Some pages describe giant storms on Jupiter, where clouds swirl into massive circular shapes spanning thousands of kilometers. Others show newborn stars igniting within dusty nebulae, like small sparks nurtured in darkness. Still others reveal the deaths of massive stars, supernova explosions scattering their enriched material across space. Each image freezes a cosmic moment, as if time itself paused for a fraction of a second, so Hubble could capture it. Hubble also documented the slow changes within our own solar system, from shifting cloud patterns on Saturn to color variations in the giant planet's atmospheric bands, to the shapes of icy moons orbiting Neptune. These long-term observations form a historical record, helping scientists track planetary cycles and study phenomena that would be impossible to notice from brief, ground-based glimpses. And because Hubble has quietly circled Earth for so many years, it has become a familiar sight that never loses its sense of vastness. From the ground, it appears only as a small point of light gliding across the night sky. But from that tiny point come some of the deepest images humanity has ever seen. Like a steadfast night watchman, Hubble speaks rarely, yet continually, opens a window into space for anyone willing to look. One remarkable aspect of Hubble's legacy is that it has produced images that carry natural artistic value. Radiant nebulae painted with sweeping colors, spiral galaxies with delicate sculptural structures, star clusters resembling embroidered patterns of glowing beads across a dark canvas. These images captivate not only scientists, but artists, designers, writers, and people who never thought they cared about astronomy. For many viewers, these pictures evoke a calming serenity, as if the universe itself is quietly inviting them to step away from the noise of everyday life. Hubble's legacy also lies in how it paved the way for future telescopes, especially Webb. Lessons about its design, its operations, its mirror flaw, and its in-orbit servicing shaped Webb's development philosophy. Without Hubble, Webb might not exist in the form we know today. The two telescopes are like two generations. One opens the path, the other widens it. Hubble stands at just the right vantage to observe invisible light, while Webb sees deeper in infrared. Together, they fill in the gaps of humanity's understanding. And through all its grand achievements, Hubble still appears remarkably simple. A telescope floating in space, circling Earth as steadily as a long, slow breath. Each orbit is another glance. Each glance is another journal entry. From that viewpoint, Hubble is both familiar and mysterious, close enough to Earth to feel connected, yet distant enough to witness what human eyes never could. It is a bridge between Earth and the deep sky, a reminder that by lifting our eyes above a thin layer of atmosphere, we were able to see wonders previously left to imagination. This section, then, gently closes the story of Hubble with the calm flow of a slow-moving stream. After 3 decades, Hubble still remains, quiet, unassuming, and leaving behind a legacy few scientific instruments could ever match. After looking back at Hubble's long journey as a quiet journal recording 3 decades of observation, the story opens into a closer realm, one where some of the most beautiful images come from within the very galaxy we live in. If distant galaxies invite us to ponder the vastness of the universe, then the structures within the Milky Way bring a sense of intimacy, as if we're opening a door right beside us to watch the processes unfolding in our own cosmic home. With its sharp vision, Hubble turned its gaze toward familiar regions of the Milky Way and revealed masterpieces that had once existed only as hazy imaginings. Among the most iconic images Hubble has ever captured in our galaxy, the Pillars of Creation holds a special place. Located in the Eagle Nebula about 6,500 light-years away, these towering columns of gas and dust rise like ethereal stone pillars glowing in starlight. But they are not stone, not solid at all. They are clouds of gas far less dense than the air on Earth. Under the intense radiation of nearby young stars, the gas is eroded into dramatic shapes, creating a beauty that feels both mysterious and majestic. Inside these towering forms, new stars are quietly taking shape. They gather gas, faint in their early light, but within those shadows lie the seeds of future suns preparing to ignite. When Hubble focused on the Pillars of Creation, the telescope's clarity revealed eroded ridges of gas, delicate filaments of dust drifting like thin curtains, and tiny bright points where newborn stars were beginning to emerge. Their beauty doesn't come from spectacle, but from the sense that we're witnessing a slow moment unfolding across millions of years. In space, where time flows at a different rhythm, every contour of a nebula is the result of processes so long-lasting that Hubble can capture only a single frozen instant in their evolution. Beyond the Eagle Nebula, many planetary nebulae in the Milky Way have been portrayed by Hubble with mesmerizing detail. Despite their name, planetary nebulae have nothing to do with planets. They are shells of gas expelled by sun-like stars nearing the end of their lives. When such a star exhausts its fuel, it does not explode like a supernova. Instead, it quietly expands and sheds its outer layers, leaving behind a hot, glowing core. That core emits ultraviolet light that illuminates the drifting shells, causing them to glow in layered rings and soft waves, like colorful clouds floating in space. Thanks to Hubble, every ring, every dust filament, every swirling structure within planetary nebulae becomes visible. Some are nearly perfect spheres. Others stretch into oval shapes or thin, petal-like extensions. Some resemble bright-eyed storms with luminous centers. Others display multiple stacked layers like rippling waves. Each shape is the final whisper of a star's transformation, a record of one last change before its remaining matter becomes part of the universe again. Farther out, the Milky Way's globular clusters appear through Hubble's mirror like cosmic jewelry boxes hanging in the night. These clusters contain hundreds of thousands of ancient stars, often located along the galaxy's outskirts. Their combined light sparkles like tightly packed gemstones forming a glowing sphere. Hubble observes them not only for their beauty, but to measure the age of the Milky Way, because the stars in these clusters are among the oldest in the galaxy. Thanks to Hubble, their structures are seen with exquisite clarity. Dense cores packed with aging stars, outer layers thinning gracefully, and slow internal motions revealed through years of careful monitoring. From Hubble's perspective, the Milky Way is not the quiet backdrop we see from Earth. It is a living ecosystem where stars are born, age, and disappear across timescales almost impossible for humans to comprehend. Hubble's images pierce through thick layers of dust, where human eyes see only darkness. In places where we see empty black space, Hubble reveals thousands of young stars. In regions of the Orion Nebula, Hubble exposes whirling disks of matter around newborn stars, structures that may one day become planets, hinting at where new solar systems are quietly forming. With Hubble's crisp detail, the Milky Way becomes vivid. It is no longer just scattered points of light, but a world in motion, breathing, shifting, slowly transforming over spans too long for us to feel. Some regions of dust are dissolving under starlight. Others are gathering into thick clouds, preparing for the next wave of star birth. These motions unfold at an incredibly slow pace by human standards. Yet Hubble patiently observes year after year, decade after decade, capturing each subtle change. Looking at these images, it is easy to feel transported into a realm that is both immense and familiar. Colorful nebulae resemble scenes from a cosmic fairy tale. Globular clusters look like suspended ornaments glowing in the dark. The great gas columns of the Eagle Nebula rise like gateways to another world. And in the middle of all this beauty stands Hubble, an unseen companion at the edge of space, sending back page after page of a journal written in starlight. The masterpieces Hubble recorded within the Milky Way are not just for admiration. They remind us that the galaxy we live in is not a static place, but a realm shaped by long rhythms, where the birth and death of stars weave together into new chapters of cosmic history. After the gentle wonders within our own Milky Way appeared through Hubble's lenses, from towering columns of dust to glowing nebulae and densely packed star clusters, the journey of observation opened a natural question. If even the marvels inside our own galaxy are so breathtaking, then farther out, at the very edges of the observable universe, what awaits us there? That curiosity led to one of the boldest experiments in the history of astronomy, an experiment that transformed a seemingly empty patch of sky into one of the most revealing portraits of the cosmos ever seen. In 1995, after Hubble had proven its extraordinary capabilities through years of operation, scientists decided to attempt something no one had dared before. Instead of pointing the telescope towards star-rich regions or bright nebulae, they selected a patch of sky so dark and empty that in nearly all previous images, it appeared as nothing more than a meaningless black void. No bright stars, no clouds of gas, no hint of anything worth observing. The region was chosen not because it was special, but because it was utterly blank. The idea was simple. If we stare long enough into a place that appears to hold nothing, could it reveal something lying just beyond every observational limit we'd ever had? For many consecutive days, Hubble was commanded to keep its gaze locked on that dark patch of sky, collecting every faint photon it could. No shifting targets, no diversions, just one tiny point of darkness in the endless night. The exposure time was longer than anything attempted in space-based astronomy up to that point, accumulating light from sources so faint that hours of observation might capture only a few scattered photons. And when the final data were processed, the resulting image stunned astronomers and the world. In that patch of sky no larger than a grain of sand held at arm's length, Hubble uncovered thousands of galaxies. Each tiny speck in the image wasn't a star, but an entire galaxy containing billions of stars. Some galaxies were round and smooth, others spiraled, others appeared stretched or warped by cosmic collisions and gravitational interactions. The light from many of these galaxies had traveled billions of years to reach Hubble, meaning that by looking at them, we were peering deep into the universe's childhood, when it was only a few billion years old. The scene was like a window into ancient time. No longer the familiar portraits of nebulae or clusters within the Milky Way. This was the universe as a whole, when it was young and still shaping itself. Faint, distant galaxies looked small and rough, like grains of cosmic dust just beginning to gather into larger structures. Some appeared merely as soft smudges, perched on the edge of detectability. Others were already well-formed, showing that even in the early universe, star formation and galaxy growth must have been far more vigorous than previously imagined. Thanks to this image, humanity understood more clearly that the universe was not a still, finished creation. It was a long, evolving process in which galaxies were born, grew, collided, merged, and changed over time. What Hubble revealed in the Hubble Deep Field was like the opening pages of the universe's history book, crude in detail, but unmistakably full of structure waiting to emerge. Hubble didn't stop at taking pictures. It also played a vital role in measuring the universe's expansion rate. By observing special variable stars whose brightness changes in a predictable rhythm, Hubble provided a reliable standard for calculating distances to faraway galaxies. Comparing those distances with how quickly the galaxies were receding allowed scientists to refine the universe's expansion rate, a value directly tied to the age of everything. Thanks to Hubble, estimates of the universe's age became clearer and more trustworthy, strengthening models of cosmic evolution. These deep observations also clarified evidence for dark energy, the mysterious force accelerating the universe's expansion. Though dark energy cannot be seen directly, its influence appears in how the expansion changes over time, reflected in the shapes, sizes, and distribution of galaxies in deep field images. Through these clues, humanity came to understand that beyond matter and light exists an invisible component dominating the universe's energy, still mysterious, still unresolved. The Hubble Deep Field was not just a photograph. It was a turning point in human perception. From a patch of sky that once seemed empty, the universe appeared crowded, dynamic, and far larger than anyone had imagined. Looking at that image feels like standing on a balcony overlooking time itself, gazing down an endless boulevard where every point of light is a story billions of years long. From this single image, people began to appreciate that every dark spot in the night sky may be hiding countless galaxies. Space wasn't empty. It was full of light too faint to reach our eyes, yet always present. Hubble proved that with patience and long enough vision, darkness reveals its depth. When those ancient rays finally touched Hubble's mirror, they became a reminder that the universe is always wider, older, and deeper than we think. And in the quiet of space, a small telescope orbiting Earth opened a door for humanity to glimpse the earliest chapters of the cosmos, where every faint glow was a whisper from the beginning of everything. After the deep portrait of the universe emerged from Hubble's long stare into a patch of sky that once seemed empty, that sense of vastness naturally opened into an even deeper mystery. If countless galaxies can hide within an area no larger than a grain of sand held up to the sky, then what lies at the centers of those galaxies? What holds them together? What shapes the motion of every star, every stream of gas, every spiral arm? Those questions lead us to one of Hubble's most profound contributions, uncovering the invisible forces that govern the movement of the entire cosmos. As Hubble observed galaxies near and far, it measured the motions of stars orbiting their centers with remarkable precision. From these orbital speeds, astronomers inferred the mass concentrated at galactic cores, And what they found was startling. The mass was far too large to be explained by any visible stars. Whatever existed there had to be incredibly heavy, yet did not emit light. Even more striking, this mass was confined within a region far smaller than any dense star cluster could account for. The conclusion became unavoidable. Nearly every large galaxy contains a supermassive black hole at its center. Hubble played a pivotal role in solidifying this conclusion. By tracking the rapid, sharply curving orbits of stars very close to galactic centers, Hubble showed that these invisible objects can weigh millions, or even billions, of times the mass of our Sun. Light cannot escape them, but their gravitational pull extends outward, dictating the movement of everything around them. Without seeing the black hole itself, its presence becomes unmistakable through the distortions Hubble captures. Stretched filaments of gas, stars whipping around at speeds no ordinary matter could produce. This discovery helped humanity understand that the heart of a galaxy is not always a blazing hub of light, but sometimes an absolute darkness where no light can escape. And from that deepest darkness, energy can be astonishingly intense. In many galaxies, the supermassive black hole is not quiet at all. It consumes surrounding matter, creating spiraling disks that flare with fierce radiation and launching jets so powerful they can be detected billions of light years away. In others, the black hole rests quietly, as if asleep, leaving only its gravitational imprint on nearby stars. Hubble revealed both states, showing how these giants shape their galaxies in profound ways. From the mystery of supermassive black holes, Hubble guided humanity toward an even broader enigma: the expansion of the universe itself. While studying distant exploding stars, far-off supernovae, Hubble uncovered something that defied expectations. Instead of slowing down with time, the expansion of the universe is speeding up. This acceleration can only be explained if there exists a hidden form of energy pushing space to expand. A form of energy that does not shine, cannot be touched, and yet dominates the universe's total energy budget. This concept became known as dark energy. Dark energy cannot be detected directly by any instrument, but its influence on cosmic expansion is unmistakable in the data Hubble collected. By measuring the distances to remote supernovae and comparing them with the speeds at which those galaxies recede from Earth, scientists detected a clear increase in the expansion rate over time. It is indirect but powerful evidence, and Hubble provided much of the key data that turned this discovery into one of the great turning points of modern astronomy. Hubble's measurements helped shape a new picture of the universe. Ordinary matter, the stuff that makes up stars, planets, and people, accounts for only a small fraction of everything that exists. Most of the universe is composed of dark matter and dark energy, invisible components that do not glow but govern motion and shape the future of cosmic space. Even though both dark matter and dark energy remain enormous mysteries, Hubble showed humanity that the universe is not only vast, but filled with unseen forces more influential than any visible light. In the years that followed, as Hubble continued to observe galaxies across many distances, its data allowed scientists to track how the expansion rate changed over cosmic time. This refined the accuracy of many cosmological models. Because of these long-term observations, the age of the universe became more precisely known, and the great questions about its future gained a stronger foundation for deeper study. The combination of supermassive black holes and dark energy revealed that the universe is not only adorned with bright clouds of gas and radiant nebulae, but also shaped by invisible forces working silently behind the scenes. The cosmos is both magnificent in its luminous structures and mysterious in the unseen powers that guide them. Through years of quietly collecting light, Hubble helped humanity come closer than ever to understanding the nature of those shadowed realms. Looking back at Hubble's role in illuminating these mysteries feels like standing at the edge of something immense, where the light shows only the first outlines. The rest remains in darkness, but thanks to Hubble's steady, patient data, we know that darkness is not empty. It holds the keys to a larger story about the universe, and it is the blend of what we can see and what we cannot, of light and shadow, that makes Hubble's journey one of the deepest chapters in the history of space exploration. A journey that carried human vision to the very edge of the observable cosmos. After exploring the invisible forces shaping the universe, from supermassive black holes to the dark energy accelerating cosmic expansion, the story of those distant mysteries naturally opens a new path. It becomes a journey not toward answers billions of light years away, but toward the small emissaries humanity once sent out from Earth itself. If deep space observations from orbit reveal how vast the universe is, there is another way to feel that immensity, by sending a tiny spacecraft into the distance, letting it become a silent witness to the long road away from home. From reflections on cosmic structure, the mind shifts gently toward the travels of the first mechanical messengers to leave the sun's embrace. The two Voyager spacecraft that set out more than 4 decades ago. In 1977, as the world was still taking its earliest steps into space exploration, NASA proposed a daring idea: launch 2 small probes, Voyager 1 and Voyager 2, to take advantage of a rare alignment of the 4 giant planets in the solar system. This alignment occurs only once every 176 years, offering a chance to use each planet's gravity to slingshot the spacecraft forward, letting them travel enormous distances without requiring large amounts of fuel. If launched at exactly the right moment, a spacecraft from Earth could sail past Jupiter, Saturn, Uranus, and Neptune in a relatively short time, and from there continue onward into interstellar space. Taking advantage of that opportunity, engineers and astronomers designed the Voyagers not merely as probes, but as ambassadors. Each carried a golden record, a gold-plated copper disc holding greetings in 55 languages, the sound of wind, of rain, of a baby crying, and music from Earth's many cultures. It also contained images encoded in binary: mountains, oceans, forests, the human body, molecular structures, and countless scenes representing the diversity of life on our blue planet. The message wasn't meant for anyone in particular. It was meant to say that if, far in the future, some form of intelligence ever found Voyager, they would know that a small civilization once existed in a quiet corner of the Milky Way. The launch of Voyager was not merely an engineering milestone. It was a moment of trust. Trust in human curiosity, trust in endurance, trust in the idea that understanding the universe begins with daring to reach beyond our own sky. Both spacecraft lifted off from Kennedy Space Center atop massive Titan Centaur rockets. As they rose, they carried not just instruments and cameras, but the hopes of a species longing to see beyond its horizon, and a message declaring that Earth once sent something of itself into the cosmos. Voyager 2 launched first, on August 20th, 1977. Voyager 1 followed weeks later, on September 5th, taking a trajectory that allowed it to catch up and pass Voyager 2. They left Earth only days apart, then drifted outward on paths so long they defied ordinary understanding. In their early days, they could still see Earth as a bright dot. Then the dot shrank. Then it became a tiny speck. Then it dissolved entirely into the star-filled background. The Voyagers were built to operate for at least 5 years, long enough to reach Jupiter and Saturn. But no one knew their mission would last more than 45 years and still continue today. Their instruments were crafted with exceptional durability. Every circuit board had backups. Every layer of insulation was designed to withstand fierce radiation from the giant planets. No one knew how long they would last, only that everyone hoped they would go farther than expected. One of the symbols that has made Voyager legendary is the golden record. The disk is mounted on the outside of each spacecraft, sealed within a thick aluminum cover designed to survive billions of years amid drifting space dust. A special stylus accompanies it, along with simple instructions for playing it, like an ancient phonograph waiting for any intelligence capable of deciphering it. This letter to the universe wasn't addressed to a specific recipient. It was sent to time itself, an acknowledgement that space is vast enough for what we launch to outlast even the Earth that sent it. As Voyager headed outward, its instruments came alive, gathering data. The first signals returned information about energetic particles and plasma waves near the spacecraft. Valuable details about the outer layers of Earth's magnetosphere, the vast magnetic bubble surrounding our planet. From that point onward, every step the spacecraft took carried humanity further beyond this protective shield, deeper into regions where the sun's influence begins to fade. Voyager 1 and Voyager 2 eventually parted ways, each heading in a different direction. One moved northward above the plane of the solar system. The other drifted south, two tiny arrows loosed from the same bow. Both carried the mission of recording whatever they encountered, for as long as their power could sustain them. Looking back at the moment they left Earth, no one could have predicted that one day the Voyagers would reach interstellar space, the dark region beyond the sun's direct influence. But from that first moment in 1977, a long, steady, improbable journey began. A journey where every second, every mile, carried with it the quiet message that humanity once sent two small spacecraft to look for answers in the vast, endless night. When those small spacecraft slipped out of Earth's orbit and began a journey with no return appointment, they entered a realm humanity had only ever observed from afar. The moment they left their home planet wasn't the destination of the mission. It was only the beginning. Everything meaningful lay ahead, where giant planets waited with raging storms, fragile rings, swirling towers of gas, and secrets no one had ever seen up close. Once they departed Earth, the Voyagers became two silent travelers moving through darkness, headed toward the largest worlds of the solar system. The first major stop on this grand journey was Jupiter, the immense gas giant with no solid surface, where vividly colored clouds sweep into long bands, twisted by the fierce currents of its atmosphere. Voyager 1 arrived there first. As it approached the giant planet in 1979, it began sending back images that left scientists and the public astonished. The cloud details appeared sharper than anything ever seen before. Immense currents coiling into massive storms, each larger than Earth itself. But nothing was as mesmerizing as the Great Red Spot, a storm that has raged for centuries, large enough to swallow several Earths whole. Voyager observed the Great Red Spot, as if staring into a vast, spiraling gateway beneath the planet's surface. Clouds curled into tight vortices, rippling patterns wrapped around its edges, shades of red and orange blended like brushstrokes in a living canvas. There was no solid ground, no landfall to anchor the scene, only wind, gas, and motion. From afar, Jupiter was imposing, but only when Voyager drew close did the planet reveal its strange vitality, its scale so enormous that one could suddenly feel the smallness of our own world with startling clarity. Not only Jupiter itself, but its moons offered surprises that reshaped scientific understanding. Most unexpected of all was Io, Jupiter's third largest moon, where Voyager discovered dozens of erupting volcanoes. It was humanity's first glimpse of volcanic activity beyond Earth. Glowing rivers of molten rock, plumes of gas shooting miles into space, all recorded through Voyager's cameras. No one had imagined that a distant moon could be so alive, so violently shaped by Jupiter's immense gravitational pull. That tidal force stretched Io's interior, generating the heat that powered its dramatic eruptions. Leaving Jupiter behind, Voyager set course for its next destination, Saturn. As the spacecraft approached the planet with the iconic rings, the elegant beauty of those icy bands came into view with unprecedented clarity. The rings appeared as thin, overlapping sheets, each composed of millions of ice fragments reflecting sunlight in delicate arcs. Their structure was so intricate that even slight changes in density produced subtle patterns. Before Voyager, people saw only a bright halo around Saturn. Voyager revealed a layered system, each ring a masterpiece sculpted by gravity and motion. Voyager also examined Titan, Saturn's largest moon. Titan is wrapped in a thick, hazy orange atmosphere that hides its surface from view. While Voyager's cameras couldn't penetrate the haze, the discovery of such a dense atmosphere sparked enormous scientific interest. Decades later, other missions would reveal Titan's methane lakes and hydrocarbon rain, but it was Voyager that first confirmed Titan as a world with a remarkable atmosphere unlike any other moon in the solar system. After Saturn, Voyager 1 curved out of the ecliptic plane and headed upward, leaving the path toward the more distant planets. Voyager 2, however, continued onward, becoming the only spacecraft in history to visit both Uranus and Neptune. These two distant blue worlds had long been seen only through Earth-based telescopes, blurred by the atmosphere. But Voyager 2 approached them directly, offering humanity its first clear view of their cold, cerulean faces. When Voyager 2 reached Uranus in 1986, it revealed a smooth, calm-looking planet with far fewer storms than Jupiter or Saturn, yet possessing a distinctly unusual atmosphere. Uranus rotates on its side, tilted nearly 98 degrees, causing its seasons to last for decades. Its soft blue color comes from methane absorbing red light. Though the upper atmosphere seems placid, the deeper layers hold crushing pressures and extreme temperatures, regions that scientists can only model, never directly observe. Voyager 2 then journeyed farther still, arriving at Neptune in 1989. There it discovered the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, but swirling above a world so cold that methane freezes into the deep blue hue that covers the planet. Wispy white clouds drifted above the storm like thin threads across a dim sky. It was humanity's first close-up look at such a remote planet, and remains the last. As no spacecraft has visited Neptune since, Voyager 2's observations of Neptune and its moons, especially Triton, with its erupting nitrogen geysers jetting through an icy surface, added crucial pieces to our knowledge of frozen worlds. These discoveries revealed that even the farthest regions of the solar system are dynamic, changing, and filled with complex processes. After passing the last giant planet, Voyager 2 continued its outward flight, becoming an unending traveler, just like its sibling, Voyager 1. What they left behind was a collection of images and data unlike anything before. The swirling colors of Jupiter, the delicate rings of Saturn, the pale blue of Uranus, the storm-torn skies of Neptune. In the absolute stillness of space, the two spacecraft drift onward, carrying with them the stories they gathered on their passage past the giant worlds of the solar system. A journey retold like a soft breeze moving through the dark, gentle enough to lull listeners toward sleep, yet deep enough to remind us that beyond our reach, there are still countless wonders waiting to be discovered. After the two Voyager travelers swept past the giant planets, past scenes so vast they seemed able to swallow Earth whole, past storms wider than worlds, their journey began to shift into a quieter, more distant realm. From the glow reflected off enormous gas planets, from Saturn's shimmering rings, from Neptune's spiraling tempest, Voyager slowly drifted away from all of it. Those detailed images of swirling atmospheres and restless moons became memories of the path behind them, while ahead lay a different kind of darkness within the solar system, one where sunlight faded a little more with every passing million miles. After its encounter with Saturn in 1980, Voyager 1 began turning away from the ecliptic plane, the flat path where nearly all planets orbit. Its new trajectory wasn't an accident, but the result of careful planning, a gravitational slingshot from Saturn that would fling the spacecraft outward as fast as possible. From there, Voyager 1 had no more giant worlds to visit. Before it stretched a growing emptiness, with the distance between the spacecraft and the Sun increasing by hundreds of thousands of kilometers every hour. As it drifted away from the planets, Voyager 1 entered a region where the Sun's influence remained, but weakened. This realm is called the heliosphere, a vast bubble carved out by the solar wind, filled with high-energy particles and a thin magnetic field that surrounds our entire solar system. Inside this bubble, the Sun still shapes everything, but near its edges, things begin to change. The solar wind slows. Particles from distant stars begin to seep in, and with sunlight too faint to brighten its path, Voyager 1 moved into a dusky frontier that no spacecraft had ever reached. In the years following its departure from Saturn, Voyager didn't return spectacular images anymore. Instead, the spacecraft sent back something quieter but equally precious: data. Measurements of energetic particles, plasma waves, and magnetic fields steadily streamed toward Earth, revealing how the environment around the craft shifted as it drifted toward the boundary between the Sun's space and the star's space. By the early 2000s, Voyager 1 approached the heliosphere's outer layers, the region where the solar wind slows dramatically as it meets the interstellar medium. It is a zone of transition, where matter and forces from both sides, the Sun and the galaxy, intermingle. There is no sharp line, no cosmic signpost. The edge of the solar system is more like a foggy coastline, a gradual blending where every physical measurement changes slowly but unmistakably. Finally, in 2012, Voyager 1 detected a profound shift. The number of high-energy particles from the Sun dropped sharply, while particles from interstellar space surged. It was the signature scientists had long awaited, evidence that the spacecraft had crossed the heliopause and entered interstellar space, the realm beyond the Sun's direct influence. There was no flash of light to mark the moment, no dramatic event, just a change in data, soft as a quiet exhale from the universe. That moment marked the first time in history that a human-made object entered the space between the stars. Voyager 1, barely a few hundred kilograms in mass, became Earth's ambassador in a region where stars sit trillions of miles apart. It no longer traveled under the Sun's protection. From that point on, its path was guided only by the faint gravitational pull of the entire galaxy. In that darkness, sunlight was so weak it could no longer illuminate anything near the craft. If another spacecraft had been floating just a few hundred kilometers away, the two would still be invisible to each other. Two shadows drifting through an endless night. Yet those same invisible cosmic rays, high-energy particles saturating interstellar space, became the very clue Voyager needed to know it had entered a new domain. Its instruments recorded a steady rise in their intensity, confirming it had left the sun's protective shell. Interstellar space is not empty. It is a thin ocean of gas, dust, and radiation, where the sun is merely one faint influence among countless others. From there, Voyager 1 continued to send home signals through its low-power antenna, transmissions that now take more than 18 hours to reach Earth. Each one carries only a small amount of information, but it must cross more than 10 billion miles to get here. It feels like a message from an old friend who has wandered far, still patiently telling us what it senses in the dark. The journey out of the solar system comes with no grand vistas, not like the spectacular colors of gas giants, or the brightness of rings, or the icy surfaces of distant moons. And yet, that very stillness makes Voyager's crossing into interstellar space profoundly moving. The moment is not just a triumph of celestial mechanics. It is the quiet extension of human curiosity beyond the world that birthed it. Today, Voyager 1 keeps traveling outward at nearly 17 kilometers per second, pushing millions of miles farther from Earth each day. It does not slow down. It does not turn. It has no destination to reach. Behind it lies the entire history of the solar system. Ahead, a darkness no one has ever seen. One day, when its power finally fades, the spacecraft will grow silent, but its journey will continue, drifting through the Milky Way for billions of years. And somewhere within that vast, cold expanse, the golden record still spins. Its engraved greetings, its whispers of wind and rain, its songs and photographs, drifting through the galaxy like a tiny stone carrying the story of Earth, traveling with a traveler that will never return. After the story of Voyager's departure from the solar system carried the mind into distant realms where interstellar darkness envelops every direction, the memory of what came before naturally becomes a bridge leading back toward the discoveries that first made the two Voyager travelers famous. Because before they drifted into the deep, star-to-star emptiness, those small spacecraft had already passed through one of the most magnificent worlds in the solar system. A world with a churning atmosphere and a moon so violently active that no one imagined such behavior could exist beyond Earth. And it was on that enormous planet that Voyager witnessed secrets forcing humanity to rethink the diversity of worlds scattered through space. Jupiter, over 1,000 times larger than Earth, is a gas giant with an atmosphere stretching like an endless sea of clouds. From Earth, its crossing bands, its mysterious red patch, and its hazy telescopic images had always stirred curiosity. But it wasn't until Voyager 1 approached the planet in 1979 that humanity saw, for the first time, the vivid, living details of Jupiter's atmosphere, almost as if looking into a world that breathed in color. The photos Voyager returned revealed that Jupiter's cloud bands were not calm, painted stripes, but fast-moving streams swirling at astonishing speeds, in many places reaching hundreds of kilometers per hour. Small vortices twisted into one another like miniature storms, stacking and colliding in patterns too complex to predict. The clouds, made of ammonia, hydrogen sulfide, and water, reflected sunlight differently depending on their composition, forming a wide palette that ranged from pale yellows to deep reds to slate blues. Among all these features, the Great Red Spot stood out most. This massive storm had been observed for more than 300 years, but Voyager provided an entirely new perspective. No longer a muted smear, It appeared as an enormous cyclone larger than Earth, rolling between cloud bands and radiating raw energy. Voyager captured the swirling layers inside the storm with such clarity that it revealed alternating motions. Some cloud layers rotating clockwise, others counterclockwise, creating the effect of a painting that never stopped spinning. Beyond the clouds and bands, Voyager also detected lightning flashing in Jupiter's high-latitude storms. These bolts were thousands of times brighter than lightning on Earth, offering a glimpse into the sheer power contained within the planet's atmosphere. The electromagnetic bursts lit up sections of the clouds like pulses inside a giant planetary engine. Yet Jupiter's greatest surprises did not lie within the planet itself. As Voyager swept past its moons, stunning secrets emerged. Among Jupiter's more than 90 moons, Io delivered the most dramatic shock to humanity's understanding of geology beyond Earth. Different from the icy moons surrounding it, Io appeared fiery and restless. Voyager saw dozens of erupting volcanoes with plumes soaring hundreds of kilometers high, spraying sulfur across the landscape and forming arcs in bright yellows, reds, and oranges. Rivers of molten rock glowed red in the night. It was the first time humanity had ever witnessed volcanic activity on another world, something no one expected from a moon so far away. The cause of Io's intense activity lies in the gravitational pull of Jupiter, along with the tugging influence of other moons such as Europa and Ganymede. These interactions constantly stretch and compress Io, heating its interior and generating enough energy to sustain hundreds of volcanoes. Unlike Earth, whose volcanic activity is driven by shifting tectonic plates, Io represents the extreme case of tidal heating, a phenomenon where gravitational flexing creates heat so intense it melts rock. Voyager also studied Io's thin atmosphere, where sulfur dioxide forms a faint, hazy shell. Though far too thin to support human life, it was a crucial clue to the moon's extraordinary geological activity. By recording the light reflected from eruptive plumes and measuring their height, Voyager revealed that Io's violent behavior wasn't rare. It was constant. Jupiter offered further surprises in the moons Voyager observed. Europa, 4 times smaller than Earth, has an icy surface nearly smooth, etched with long fractures running across it. Though later missions would bring the strongest evidence of the ocean beneath its crust, Voyager was the first to capture the unusual nature of Europa's surface, leaving behind a question that would echo through decades of research. What lies beneath that frozen shell? That question eventually became the foundation of the idea that Europa might harbor a subsurface ocean capable of supporting life. Ganymede and Callisto, 2 other Jovian moons, were also seen in greater detail than ever before. Ganymede, the largest moon in the solar system, showed a mixed surface of ancient dark regions and younger light terrain, hinting at tectonic activity. Callisto, by contrast, appeared ancient and untouched, its cratered surface revealing a world frozen in time. Thanks to Voyager, Jupiter was no longer a distant planet with mysterious cloud bands. It became a world of intense activity, where atmospheric, electromagnetic, and geological processes unfolded continuously, dynamically, and far beyond what anyone had once imagined. The planet and its moons were no longer faint points in the sky, but an entire living system, each part carrying its own story. As Voyager moved on from Jupiter's realm, the images and data it sent back became the foundation for decades of research. Jupiter's secrets, its atmospheric layers, its storms, its volcanic moon, became essential pieces of humanity's understanding of planetary diversity. And in the quiet of space, the 2 travelers continued drifting outward, carrying with them the memory of that giant world, one of the key stepping stones that eventually led the Voyager mission out into interstellar space. The secrets Voyager unveiled around Jupiter, from its swirling, vividly colored storms to the fierce volcanic activity on Io, not only broadened humanity's understanding of gas giants, but also created a natural flow toward the next chapter of its journey. The encounter with the most elegant planet in the solar system. After leaving the turbulent realm surrounding Jupiter, the two mechanical travelers moved toward a place adorned with delicate rings, shimmering as though woven from ice and dust. A place where the beauty of gravitational balance forms one of the most breathtaking scenes humankind has ever witnessed. Saturn had long been known through ground-based telescopes, though only as faint streaks, never detailed enough to reveal its true structure. But when Voyager 1 and Voyager 2 approached, the luminous rings around the planet finally appeared with crisp, pristine clarity, like threads of ice arranged by the invisible geometry of physics. Nothing else in the solar system resembled this beauty. Thin, sprawling rings stretching hundreds of thousands of kilometers, yet only tens to hundreds of meters thick, made from millions of pieces of ice that caught and reflected sunlight in subtle, dancing patterns. As Voyager drew nearer, those bright bands were no longer a single ring, but countless narrow layers. The A ring, the B ring, the C ring, and natural gaps such as the Cassini division. A soft, dark pause etched between two glowing arcs. Voyager revealed that each ring consisted of countless icy fragments, from dust grains to house-sized boulders, each moving along its own orbit while still following the exquisitely coordinated pull of gravity. Tiny collisions between the icy particles created a soft shimmer, like glitter drifting across an endless black canvas. Beyond the luminous rings, Voyager also observed Saturn's gentle cloud bands, where bright and dark streaks formed more orderly layers compared to Jupiter. The planet's atmosphere, composed mostly of hydrogen and helium, glowed with a pale yellow tint shaped by ammonia haze. The slow, steady movement of the cloud bands created the impression of a calmer world than Jupiter. Though deep below, storms still churned according to their own hidden rules. One of the most striking aspects of Saturn is Titan, its largest moon. Voyager saw Titan wrapped in a dense orange haze, so thick that the surface beneath remained completely hidden. Although the spacecraft's cameras could not peer through the clouds, Voyager detected that Titan had an atmosphere thicker than Earth's, mostly nitrogen. This discovery revived a long-standing curiosity in astronomy, for Titan had been considered a kind of frozen early Earth, a place where complex organic molecules might persist under frigid conditions. Though Voyager could not yet reveal Titan's face, it laid the foundation for the Cassini-Huygens mission decades later. After capturing Saturn's poetic beauty, the paths of the two spacecraft diverged. Voyager 1 veered upward out of the plane of the solar system, while Voyager 2 continued its grand journey outward toward the most distant regions any spacecraft had ever visited. And it was Voyager 2 that became the only spacecraft in history to fly past both Uranus and Neptune, the two icy blue worlds at the outer fringe of the solar system, where sunlight dims to little more than moonlight. Uranus appeared before Voyager 2 as a soft blue sphere, its atmosphere smooth and muted. The spacecraft revealed a world tilted almost completely on its side, spinning like a slow rolling ball along its orbit. As a result, the seasons on Uranus last for decades, one hemisphere facing the sun for years before giving way to the other. Though its appearance seemed calm, Voyager discovered winds faster than anything recorded on Jupiter or Saturn. The planet's gentle blue hue came from methane absorbing red light, leaving behind a cold, serene glow. The moons of Uranus held surprises as well. Voyager photographed Miranda, one of the strangest moons in the solar system. Its surface fractured into towering cliffs, deep valleys, and patchwork terrain that looked as though it had been shattered and stitched back together from pieces with different ages and histories. Voyager 2's journey carried it on to Neptune in 1989, the final major stop of the Grand Tour before the spacecraft continued into interstellar space. And here, Voyager witnessed one of the most dramatic storms in the solar system, the Great Dark Spot. This enormous storm, nearly the size of Earth, raged in an atmosphere so cold that methane formed icy crystals. White methane ice clouds drifted above the storm, creating delicate bright streaks set against Neptune's deep sapphire backdrop. This scene combined intensity and stillness in a way unlike any other. A storm powerful but not heated like Jupiter's Great Red Spot, rather cold, deep, and velvety, an almost silent whirl. It felt like watching a storm sketched in the dark blue tones of an ocean at night, moving slowly but filled with immense strength. One of Voyager 2's most memorable encounters at Neptune was Triton, the planet's largest moon. Triton's surface, coated with nitrogen ice, looked pale and serene, yet it was not static. Voyager recorded plumes of gas shooting kilometers into the thin atmosphere, the result of liquid nitrogen beneath the surface warming just enough to burst outward. This was the first time scientists ever witnessed cold geysers on such a distant world. Triton's retrograde orbit, circling Neptune opposite the planet's rotation, suggested that this moon might once have been a free object captured by Neptune's gravity. These icy worlds carried a graceful, lonely beauty, unlike the turbulence of Jupiter or the elegant radiance of Saturn's rings. Yet it was this quiet remoteness that made them such meaningful stops on Voyager's path. Every observation Voyager 2 made from those far edges of the solar system became a gentle reminder that life, if it exists elsewhere, may take forms far beyond anything humanity has imagined. The voyage through these frozen worlds was like a long, calm pause in the cosmic symphony, where soft blue hues met dim sunlight, where cold storms turned slowly, where moons breathed faint plumes beneath the pale glow of a distant sun. And from there, the spacecraft continued toward the limitless darkness ahead, carrying with it stories no one had ever heard before about the beauty that lives at the outer rim of the solar system. After the icy worlds at the outer edge of the solar system slowly slipped behind, Voyager's journey entered a phase where no planets stood ahead. No more sweeping views of deep blue storms, no more cold geysers rising from Triton's frozen plains. From that moment on, the path carrying the two travelers out of the familiar regions of the solar system became quieter, wider, and filled with a loneliness that no photograph could truly capture. Yet it was this silence that opened a different depth to the story. Not one grounded in grand visuals, but in reflection about humanity's place in the universe. When Voyager 2 sent back its final data from Neptune, both spacecraft began the portion of their mission in which imaging and planetary exploration were no longer the goal. They became silent ambassadors, venturing into a region no human-made object had ever reached. All the brilliant scenes they once recorded now lay behind them, while ahead stretched a vast, dim expanse where the sun's light faded until it became almost indistinguishable from the distant stars. And in that darkness, one of humanity's most iconic moments was about to unfold. In 1990, when Voyager 1 was more than 6 billion kilometers from Earth, NASA scientists made a request that was simple yet profound. They asked the spacecraft to turn its camera around and take one final photograph of home. The moment wasn't meant for scientific discovery. It was meant as a reminder that everything that existed, every civilization, every story, every sorrow, every hope, was contained within a single tiny point of light. When Voyager 1 sent the image back, Earth appeared as a pale blue dot, so small it occupied only a sliver of the frame. This was the pale blue dot, a picture possible only because the spacecraft had traveled far enough for our world's light to shrink into a single speck floating within a sunbeam. That faint dot hung in the darkness, no larger than a fleck of dust beside a streak of radiant light. And from that fragile point, every story of humanity had begun. In that image, Earth became a reminder that no matter how far we stretch our understanding, our place in the universe remains far more modest than we imagine. It wasn't just a photograph. It was a reflection of our own awareness. A small planet in a vast darkness, beautiful yet fragile, bright yet easily swallowed by the surrounding cosmos. After that moment, Voyager 1 continued to drift away. Its cameras were shut down permanently to conserve power, and from then on, it would send only invisible data. Energetic particles, background radiation, plasma waves, the signatures of an environment humanity had never directly visited. As the spacecraft approached the boundary of the heliosphere, another milestone in scientific history quietly prepared to unfold. The heliosphere, a giant bubble created by the solar wind, encompasses the entire solar system and shields it from much of the cosmic radiation outside. As Voyager 1 neared its border, its particle detectors began recording dramatic changes. A sharp drop in particles coming from the sun and a steady increase in high-energy particles arriving from interstellar space. These changes were the first hints that the spacecraft was approaching a boundary no human-made object had ever crossed. In 2012, Voyager 1 crossed the heliopause. There was no burst of light, no visible sign, just data confirming one extraordinary truth. The spacecraft had entered interstellar space, where the solar wind no longer dominated and particles from distant stars formed the rhythm of the surrounding environment. It wasn't a dramatic moment. It felt more like a subtle shift in the cosmic breeze. But to humanity, it marked the first time our technology had passed beyond the natural limits of the solar system and into the vast domain of the Milky Way, like a tiny grain of dust drifting into an endless ocean. In interstellar space, everything became quieter still. There were no planets to glow, no icy moons to sculpt landscapes, no atmospheres to paint colors. There was only thin interstellar gas, few atoms in each cubic centimeter, and cosmic rays whispering like distant rainfall on a metal roof. The signals Voyager sent back were subtle vibrations of plasma, measurements of particle densities, traces of electric charge, all painting a portrait of a place utterly unlike anything humans had known. Voyager 2, slower and traveling along a different path, crossed into interstellar space in 2018 and sent complementary data, helping scientists better understand the structure of that invisible border. Though pointed in nearly opposite directions, both spacecraft drifted like two small leaves on the galactic wind, carrying stories from the planet that built them. These two small machines, each only a few hundred kilograms, are now enduring ambassadors in the dark. After their nuclear power fades in the coming decades, they will fall silent. No signals, no measurements, no more conversations with Earth. But they will continue moving through space, unimpeded except by the faint gravity of the galaxy. And the golden record, the greeting from Earth engraved with sounds, images, and hope, will continue to spin quietly. It may drift for millions of years. It may never be found. But its existence is a whisper of affirmation. Humanity once lived, once wondered, and once sent something outward with the hope of being heard. Webb's discoveries of the universe's earliest moments, Hubble's deep images from the edge of the observable cosmos, and Voyager's voyage beyond the solar system, all merge into a single story. Humanity has always longed to know where it stands in the universe. And though the answer remains elusive, each of those steps opened the first few doors. In the stillness of sleep, that story continues to expand like slow starlight from a distant sun, reminding us that the journey of discovery has no end.